Hello, my name is Rafael. I'm one of the authors of the BIM Handbook, and I'm here today to tell you a little bit about the new third edition. It's a real pleasure for me to be here, albeit only by video, at the BuildSmart Forum in Seoul, Korea. So thank you for the invitation. I will try in the next 20 minutes to give you a good idea of what's in the book, what things have changed over the past 10 years, and what we can expect going ahead in the world of building information modeling. So without much more introduction, I'm going to move over to the computer and tell you more about it. So let's talk about this. 10 years of the BIM Handbook. The first edition was published in 2008, and now in 2018 we're about to see the third edition. So what has changed in BIM over the last 10 years? What new technologies are available, and what new processes have developed? Have any of the predictions we made become reality? Well, let's start with a brief history of the handbook itself. The first edition, as I said, was published in 2008, and the second edition in 2011. We're now up to the third edition, which will be available from the 1st of August. The book has also seen a number of translations. The first edition to be translated was into Korean, and that appeared thanks to Professor Gong Li in 2009. In 2014, the first Portuguese edition was produced under the leadership of Professor Eduardo Toledo Santos in Sao Paulo, in Brazil. In 2014, again came the second edition, again in Korean. The first Italian edition was prepared in 2016, and the first Chinese edition was produced in Mandarin in 2017. Now let's perhaps have a quick look at building information modeling itself. One of the most significant papers concerning the idea or the concept of building information modeling was called The Use of Computers Instead of Drawings. And Chuck Eastman, one of our co-authors, wrote this paper in 1975 in the AIA journal, American Institute of Architects. And some of the things that he said here were extremely prescient. For example, he said that designing would consist of interactively defining elements, that the elements would automatically be consistent, and all drawings derived from the elements would be consistent. Any type of quantitative analysis could be coupled directly to the description. That the modeling would provide a single integrated database for visual and quantitative analyses, and even for testing spatial conflicts. We all know very well now about clash checking, about producing drawings from the same model, about an interpretive model, and so on. But in 1975, these things were certainly not understood at all. So we can see, even further, going further, later one can conceive of a building description system supporting automated building code checking. Perhaps this was prescient to the extent that even now we are still struggling to make this a reality. But as you'll see later in this presentation, with artificial intelligence and machine learning, these things are now becoming a reality. So what is the nature of building modeling? In these models here from Singapore, from the Maple Tree Business City 2 project, which is a new case study in the handbook, you can see 3 different discipline models all combined into a single model. So we really are starting to see this idea of the model being a prototype of the construction itself. You can see here, for example, in this slide, that what we used to do before BIM was we would design, we would construct or build, and then on the site we would discover all the errors. And once we'd ironed out all the errors in the building, we still discovered that there were functional failures, meaning that the building did not meet the needs of its designers or of its owners or of its occupants. And then, of course, in many cases, we had this problem, lawsuits, which followed all those errors and functional failures. When we began working with BIM, and I would say that this was the thrust of the book in 2008, it became clear that we could get rid of a lot of the errors in design by coordinating among models. and especially clash checking, which we might call the low-hanging fruit, became something really significant. But still, the construction industry at the time just suffered functional failures. Buildings still did not perform in the way that they should. Energy analyses in particular were found to be not entirely reliable. Many buildings, even some that were featured in the first and second editions as case studies with great hopes, ended up disappointing and producing energy performance that was well below what they're being predicted to do. And so, for example, in the San Francisco Federal Building, air conditioning had to be installed retroactively. Nowadays, what we see in many more countries and in many more industries, construction industries, is that apart from doing the BIM modeling and the geometric modeling, we're seeing that people are doing a lot more simulation. And while we wrote about this in the first and second editions, we have made this a much greater thrust in the third edition. The idea being that you really can create a virtual prototype of the building. You can identify functional failures as well as errors, with then creating the construction as error-free and the building as good performance as possible. And this, we think, is the real benefit of virtual design and construction. So what has changed and what's new in the book? Well, for a start, we have a new author team. Professor Gong Lee of Seoul, Korea, has joined the team, and he has taken a very strong role in. You probably are all aware that BIM research has really taken off in terms of its extent and its influence. If you were to go to Google Scholar and you were to search for building information modeling for the full set of 3 words, then this is what you would see if you counted the number of articles or publications. It includes books, journal papers, and conference papers published around the world in every individual year. And you can see that already in 2016, we passed 4,000 articles per year, which is an enormous number, and it continues to increase. It's interesting that this only really took off from the year 2004-2005, but when the first edition of the handbook was published, there were still less than 1,000 articles per year, and that's more than quadrupled in the time that we are now. I guess that one of the important things that we've done in this edition is we've made a very big effort to identify and explain what is a BIM tool, what is a BIM platform, a BIM environment, and a BIM server. And I think that the key here is that we recognize that you can have a platform that has many and varied tools within it. That also libraries of objects can exist within the platform, as we might think of families within Revit. Or they might exist in external libraries, as you might find in MEP content or other commercial libraries where are external to any individual platform. Another thing that's changed really radically since 2008 is that we now have a plethora of BIM guides, of mandates, of roadmaps in different countries. Along with those go maturity models and measures to tell people where they are and where they are along the process. And in fact, chapter 8 is an entirely new chapter in the book that deals with the guides, the mandates, the government mandates, with roadmaps of different kinds, and with maturity models. The chapter also deals with BIM education and with the kinds of employment opportunities that BIM offers. You can see, for example, as if we quickly look at this notion of BIM regulation and support, that many countries have adopted the British approach, which you see here with British standards and the BIM levels that have been defined, where most countries are still somewhere within the rubric here of BIM level 2 and are still struggling to understand how they move over to BIM level 3, where the emphasis is on the information, on the integrated interoperable data, and not so much on the models per se as we know them today. One of the great examples of a BIM roadmap is this roadmap from the UK, which is for the High-Speed Rail 2 project running up the western side of the UK, all the way from London all the way to Manchester and north. You can see that they have laid out all of the different ways in which they plan to use BIM for different aspects of the design process and to experience savings as they go through that. And while obviously I can't go into every detail on the slide, you have the sense that this really does lay out their sense of progress and of increasing ability to use the BIM tools, platforms to achieve the cost savings and efficiencies that they hope to do. Another thing that's changed is that we're spending a lot more time and investing a lot more effort in solving this problem of being able to scan existing infrastructure, translate it into 3D objects, and then transform those 3D objects into useful, information-rich BIM models. One of the projects that's pushed this idea much further ahead is called Seabridge, and this was a European Union project under the Fabrication umbrella, which really went very far in being able to scan a bridge like this one, identify the 3D objects that are within it, and then turn those into BIM models that are native models together with all the connections and the other rich semantic information that we need to be able to use. And so you can see that that turns into a BIM model, something like that, which is dimensionally accurate, but also semantically rich. Already in the first edition, we spoke a great deal about the ideas of fabrication and of being able to shift as much construction off the site as possible. In this slide, you see an example from the book in chapter 7, where you see the BIM model on the bottom left. You then see a worker in a fabrication shop preparing pipe spools. They're assembled on racks and delivered labeled to the site, where it becomes a matter of installation and erection rather than one of fabrication and manufacture. And we believe strongly that BIM is going to contribute greatly in this area. There is also a new case study in the book on the St. Joseph Hospital in Denver, which strongly supports the ideas, including a lot of figures and numbers of the return on investment for fabrication supported by BIM. 4D scheduling, virtual design and construction, and in particular the ability to understand the procedure of construction has become more emphasized in the new version of the book. Chapter 7 deals with, Chapter 6 and 7 deal with construction contracting and fabrication. This is an example from the Hyundai Motor Museum, which many of you may well be familiar with in South Korea. And you can see that they were able to very carefully plan the erection of steel to start from 2 directions and without creating the conflicts or mismanagement that can become common in projects of this kind. Another example comes again from the Maple Tree building in Singapore, where scheduling of formwork, scheduling of reinforcing tower cranes, etc. is all done now through the model. Already in 2008, we had the sense that lean construction and BIM would have a confluence and would be able to work together at some time. We've seen this grow very much over the past 10 years, and this has become very significant. Building model is increasingly used on site to reduce cycle times, to reduce variation, to improve the quality of information, and all of these things significantly not only reduce waste in construction, but they also improve flow. You can see an example here. This is a project from Israel, where I live, from a new development in Rosh Hashanah, built by the Tidal construction company. You see on the left a typical floor production plan, where it's color-coded according to the different concrete pours that will be done, and then by measuring the length, area, and volume of concrete, area of formwork, volume of concrete in each section, the pours themselves are defined in cyclical fashion. And in this particular project, these were simulated out using 4D based on, and the result was a reduction in cycle time from 9 days per floor to 6 days per floor, with formwork being shifted from among 2 buildings which were very similar, albeit not entirely identical. At the same time, the crew was reduced from 26 to 24 workers. There have also been a much greater investment in building modeling on the part of construction component suppliers. In this case, you see formwork produced by Perry in Germany, and this is the top of a bridge pier, and they're now able to provide model objects of very high resolution and detail with which contractors and others can plan the progress of construction and observe any kinds of issues or clashes and so on, both in space and in time. Another aspect that we've paid far more attention to in the 3rd edition than in either of the previous 2 editions is the subject of facility operation and maintenance. And in particular, the challenges in moving information from the last stages of construction into the stages of operation, maintenance of a facility. We have in Chapter 4, which deals with the owners, increased greatly the coverage of companies and asset owners who are using facility operation and maintenance based on BIM. There are also no fewer than 3 case studies of major projects, an airport, a hospital, and a research building, all of which have used facility maintenance. These images give you a quick example. These are from Medina Airport. They're courtesy of TAV Construction in Istanbul, who are the managers of the project and the operators of the airport. And you can see the airport building, a photograph above, but you can also see all the detailing of the systems in that building below. I should add that these systems were all modeled after the building was complete, and the lessons learned are brought through very thoroughly in the case study of Medina Airport. So briefly, what can we expect next going into the future? Well, of course, augmented reality is becoming far more available. There are many startups around the world who are offering these kinds of tools. In this slide, you see an image courtesy of DCA and Shimizu in Singapore from the Maple Tree project, another one of the case studies. You're seeing on the left-hand side the iPad with the systems exactly as they exist above the ceiling. And here, an image courtesy of Trimble, where you see a construction worker using a Microsoft HoloLens to superimpose the partitions that they're going to build on top of the construction site itself. And these tools also are improving rapidly in their ability to be used on a site. I did mention earlier the linkage between lean construction and BIM, and production control, production planning and then production control are very much lean construction ideas that have been very well developed in the lean construction community, and now they're being implemented with BIM. In this image, you see on the left side a reporting screen from a mobile phone app, which is part of the VisiLean software. VisiLean combines the best of BIM and last planner scheduling and other aspects of lean construction. It grew out of the CanBIM project, which was an experimental work in 2008 and 2009, and all of these are now becoming commercial systems. On the right-hand side, you see a trade worker and another control application, which are courtesy of Fira in Finland, who are developing very similar tools for workers to use in bathroom renovations. One of the more interesting things and more futuristic that we see coming out of the research labs is this idea, which is a joint project of Bourget Construction in France and a number of research labs. You can see that the idea is to create tools for a construction worker where they are actually wearing the computing. Perhaps things that we predicted in 2011, which took some time to bear fruit, and now 2018 is no longer a future prediction, but in fact a description of something that's happening right now, is that artificial intelligence in its various forms, including rule inferencing and machine learning, are being brought to bear both for semantic enrichment and for code checking within building information modeling. The image that you see here expresses the idea from the first work that was done on semantic enrichment, where the input was an IFC file, but a very basic IFC file. You see that it contains only object classification, object identity, properties, and solid geometry. But then it undergoes the processing through a semantic enrichment engine to add on many other things: parametric geometry, aggregation relationships, functional relationships like things which are connected to one another, various parametric constraints that reflect how things should behave in relation to one another. and also the ability to rebuild occluded geometry where that might have been, for example, in a use case where we have a point cloud, we've generated a 3D model from a point cloud, and now can we reconstruct a native BIM model? Well, if we have a good understanding of what a beam that was partly occluded should look like in its remainder, then we can make a very good guess and add those into the model in an earlier slide. Another aspect of this AI semantic enrichment is BIM, and as I mentioned, the ability to use ruling, inferencing, and machine learning, is that we believe that AI and semantic enrichment will enable us to do a number of things which we haven't been able to do up to now. For example, compiling BIM models from point cloud data, as I mentioned in the previous slide, but also a more fundamental approach to the interoperability problem. We hope to turn this into a problem for the receiver rather than the sender of BIM information. A receiver of information, in general, knows exactly what they want and what they need. That receiver may be an architect and engineer, but more specifically, they may be a specific software application being used by an architect or engineer. If, for example, we wanted to do code checking, whether with Solibri, Smart Review, Inglicaro, or other systems, what we first need to do is add in enough smart information to the model to enable it to use and to process. That's the semantic enrichment. And we believe that this can be automated to a great extent, which will then mean that models produced from more or less any system may in the future be able to be imported into any other system, where the importing system will add in any implicit information that was absent from the IFC or other file it received. Perhaps to sum up this area of what we see coming ahead, we can look at the slide of BIM in 2030, which was compiled by Gong Li and his team at Yonsei University and features in Chapter 8, in Chapter 9 of the BIM Handbook. And you can see that it begins here with early coordination BIM over here. It then proceeds on to two-track BIM, which had to do with the idea that people were doing different models in parallel in the early 2010s, and then full BIM, integrated BIM, BIM 3.0 toward the end of the 2010s. And now, as we look ahead to the 2020s, perhaps the next step will be a much deeper integration of Lean and BIM, but going beyond that, much more emphasis on artificially intelligent BIM, where BIM really will become the platform for many other functions that we're not able to do now, but which I discussed in the previous slide. Finally, what we have new in the BIM Handbook in the 3rd edition are 12 entirely new case studies. All of them have been replaced. And let me simply show you a single slide from each of them. This is the Dublin New Children's Hospital in Ireland, where they've extensively used modeling to communicate with the stakeholders in the project. This is an image of the Louis Vuitton Creation Building in Paris, France, one of Frank Gehry's unique, masterpieces, which I think it's fair to say could not have been built without BIM. I mentioned earlier the St. Joseph Hospital project in Denver, Colorado. It was built by Mortenson Company, and the key feature of this case study is its big emphasis on prefabricated modules. Victoria Station in London, UK, is an underground station. You will see here strong use of BIM for geotechnical work, for tunneling, for platform design, for MEP design, and so forth. The North Hills Residential Hall in Singapore was built on the Nanyang Technological University campus. What's unique about this project is that it is entirely prefabricated. Whole room modules were produced first in Shanghai as structure, and then fitted and finished in Singapore, and then simply hoisted into place around pre-built concrete cores for the elevator and stairwells to very rapidly generate these buildings. The Howard Hughes Medical Center in Chevy Chase, Maryland, is an example of a research facility where facility maintenance is being applied and implemented to a great degree. Same is true of the Stanford University Medical Center in Palo Alto in California. Again, an example of an excellent use of BIM for facility maintenance and operations. Hello, I'm back again, Rafael. I hope you enjoyed the talk and found it interesting, and I hope you will also, of course, find the BIM Handbook 3rd edition of interest. It should be available from August 2018. While I'm here, let me also tell you about another book that you might find interesting, which deals with lean construction and BIM and their adoption together. It tells the story of a unique company called Tihal, who set about adopting these two innovations in construction simultaneously and the kind of benefits that they were able to get from it. This is one of their buildings. But the book also tells the case studies of Skanska in Finland, of Lease Crutcher Lewis in the northwest of the US, headquartered in Seattle, Washington, and of Fira, or a company in Helsinki, Finland. And so I hope you will find that one of interest too. So thanks once again for the invitation to speak to the BuildSmart Forum in Seoul, Korea 2018. And of course, a very special thanks to my good friend and colleague, Professor Gong Li, a co-author of the BIM Handbook, for the personal invitation to speak to you today. Thank you very much. Bye-bye.